Welcome everyone to the next video in the vibration series. I hope you enjoyed last video. This video is just leading on from some of the basics we learned in last video about free vibration. This is only about free vibration, this video, and we're going to be analyzing a system over here under free vibration. And we're actually going to be doing some math today and trying to answer this question here, which is, how do we determine the mass displacement x at any time t? So we've got our coordinate system here, x of t, and what we want to know is we want to know this x of t value for any time t. So as the mass is oscillating up and down, we want to know what the displacement is at 5 seconds, 10 seconds, and so on. So we're going to be analyzing this. So to analyze this system, what we want to do is we want to find the forces acting on it. So the first step we do with anything in mechanics is we draw a free body diagram. So I've drawn this free body diagram down here. And as you can see, we've just got our mass and we've just got this force here, K times X. Now I'm just going to briefly explain what I've done here. K times X is the spring force. So K is just the spring constant, which is in newtons per meter, and X is just in meters. So what happens is when we do the unit balance of here, we get the meters cancelling out and we just have the newtons left, which is our force. So this is actually a force. Now, the way you determine, and this is quite important because it's easy to get wrong, the way you determine this arrow is that from our predetermined direction here. So we are taking x of t as positive down. So when I'm drawing my free body diagram, I want to pretend that I'm taking this mass and I'm moving it down. And if I move it down, the spring is going to push back against the mass. It's going to push up. And this is important because if you get the direction of this vector wrong, you're going to get the wrong answers. So when you're determining a free body diagram, look at how you've assumed your directions, pretend you're moving the mass down in that direction, and then ask yourself, well, which way is the spring force acting? Okay, so basically now we do what you've probably done many times before. We use Newton's second law. Sumter Forces is equal to ma, which is equal to mass times x double dot, which is just the double derivative of displacement. So because we're assuming that x down is positive, we're going to do the same here, little arrow here. So I always like to denote there so I don't get confused. So now it's quite simple. All we have to do is we say, well, we have k of x pushing up. So that's going to be negative because this arrow is going up and this arrow is going down, which is the way we've denoted our positive. So we've got negative kx is equal to mass times acceleration double dot. Now rearranging this, we're just going to get m double dot plus, because we move this around to the other side, kx is equal to 0. This is our equation of motion. So as this mass moves up and down, this equation here describes its position. So we haven't fully evaluated it yet, but when we do, we can solve this equation to find x of t, which is what we're looking for, because this will give us a value for the displacement at any time t. Okay, and that's pretty much it. We've got our equation of motion. Now all we need to do is solve. Now, I'm not going to solve for x of t in this video because I just want to hop over back to the free body diagram for just a moment to explain an important concept that lots of people get snagged on. And that is that I'm not including gravity in this free body diagram. You can see that there is no mg pointing down. I don't have this vector mg, which is the weight of the mass. And this is really important because this is counteracted by the spring because we're assuming that the spring is at rest. We're assuming the mass is at rest. So I'm just going to hop down here and I'm going to draw out some more diagrams and we'll go through them together. Okay, so I've just come down here and drawn two different free body diagrams. Now, the key difference is we are drawing them at different times. So in the first free body diagram I drew previously, that was just any time t, the mass is moving up and down at any time. So what I've done this time is I've broken it down into two different free body diagrams at different times. And I'm going to show you why the weight of the mass does not change our Sumter forces. Now, you don't have to know this, but it is a nice little thing to see at least once so that you don't get confused by it in the future. So on the left here, we've got static equilibrium, which means that the mass is completely stationary and has compressed the spring by a certain amount because of its weight force acting on the spring. So what we can do now is we can come down and do our Sumter forces again. So we're going to assume that this is positive, which is valid because of this coordinate here, our XO, and we're just going to do Sumter forces. This is a little XO is equal to mass times acceleration of XO. Now, XO is a completely different coordinate to X. We're just denoting two different scenarios. So what happens is, let's do the Sumter forces. So we're going to have mg's going down, so it's going to be positive mg, and then we're going to have minus k xo is equal to mxo double dot. Now, static equilibrium means that our mass is completely stationary. So if our mass is completely stationary, the double derivative of displacement, xo, acceleration, has to be zero. There can't be any acceleration. So what we have is we have zero. So when I rearrange this equation, all we have left is that k xo is equal to mg. I just bring this around the other side and flip it. So what we have now is we have the force acting upwards on the mass, kxo, is equal to the force acting downwards on the spring, which is mg. So that's really nice. So we just leave that there, and then we come over to the other side here, and at any time t, we have to include t is equal to 0. So what we do is when we're doing the forces, we have xo in this bracket here, and then at any time we have this x distance. So that's why we have this combined in here. Now, I'm just going to draw off to the side to make sure we don't have any confusion here. I could have drawn it like this. One arrow up from t is equal to 0, and then another arrow up for t is equal to anything. And this one here, t is equal to anything would be x, and then t is equal to 0 would be xo. And now because they're both on the same spring, the k's are the same, and then we just group them together. And that's what we have. And now there's just 1 mg. So I'm not adding these two together. That's important. It's not 2 mg. I'm just including this initial force that we have at t is equal to 0. This mg doesn't change. It's the same here at both times. Okay, so similarly, what we do is we just do our Sumter forces again. Positive down, and then this is just in the x direction, is equal to mx double dot. Now, because this is t at any time, we can't assume that we're in static equilibrium. We can't assume that the mass is stationary. So this is going to be a real number. So we just do our Sumter forces. mg is going down, so that's going to be positive. And now k brackets xo plus x is going up, so this is going to be negative. And that's just equal to mass times acceleration. So we come over to this side and we see, hold on, kxo is equal to mg. So let's just expand this out. mg minus kxo minus, just multiplying the k through, kx is equal to mx double dot. So what we do is we just substitute in our mg. mg minus, now kxo is equal to kxo, which is equal to mg, which is equal to mg minus kx is equal to mx double dot. So I'm sure you can see that our mg's here are going to cancel because they're exactly the same. And then all we're left with is we rearrange, we are left with mx double dot plus kx is equal to 0. And this is the exact same equation of motion we had before. Equation of motion. And this just shows that the weight of the mass is negligible because it counteracts. So if we include it or don't include it, it doesn't matter. We're going to get the same answer. It's just that you have to do a lot more work to get the same result. So I would strongly recommend leaving out the weight force in vibration problems. So in the next video, we're going to solve our equation of motion down here. This equation is a second order differential equation, which is homogeneous. So if you've heard any of those words before, or even if you haven't, go to the next video and we'll go through it together. Please don't forget to like and subscribe so I can bring some more videos to you guys. Thanks for watching, and I'll see you in the next video.